Okay, so our tutorial is about neurosymbolic, customized, and compact copilots. But basically, it is about imagine basically that you have a bunch of users that engage with AI system, and the copilots is your gateway to interaction with the copilot sits between the human users or people affected by through the use of AI technology and the AI model, the one that supports all the decision making, all the processing for AI. And to a good extent, we'll talk about that core technology, the next generation of post-generative AI models, why we need them, and how we build those models, and then how we deliver the advanced capabilities of these new AI models for some fairly advanced applications. Okay, and why is this not advancing? The slides. That's only okay. So we have four components of this, four parts in this tutorial. So first, I'm going to introduce this topic itself: neurosymbolic, customized, and compact copilots. So current language models, I think most of you and probably all of you are well aware of how they work, and they are probabilistic in nature. That works fine for some cases, and especially when you're harnessing the power of large data, that works very well. And this language models predict, based on context-specific distributional mappings. Although some of us who come from who have worked, for many years in symbolic AI, the word context has many meanings actually. And context in the context the way we define and utilize context in symbolic this representation versus one in the distributed semantics, they're different. Anyway, I won't go into that detail, but indeed, this large language models or generative AI has been successful in a class of application. But I think way too much is made out in terms of really what problems they solve. They, in my view, solve a part of the problem, where AI can play an important role. Particularly, I will describe this as they are good in most part for information assistance. So you're done question answering, you need help with coding, and especially content generation. There's a paper, I don't think we are citing it here. Yeah, there's a paper actually where they analyze 1 million chat GPT prompts and found what kind of applications ChatGPT is being played for. And really the content related applications and question answering came out among the top 3. Number 2 was sexual role playing. So that's fine. For content kind of issues, this is good. But there are many the applications that add real value to society, to industry, to enterprises are typically decision-making applications, right? And for that, that involve planning, reasoning, cognition, this kind of stuff, they are not very good at, right? Language models are not very good at. There are extensive discussion on how they fail with robust planning, in reasoning, and so on and so forth. It was Daron Acemoglu just this year won Nobel Prize in Economics. He was one of the 3 winners, persons named. And he said AI can do only 5% of the jobs. So the AI, by that he meant the generative AI as it is now and probably practiced. And just I think a month ago, Gartner came out with the pretty strong headline saying that all the growth in the next 3 years will be in enterprise AI applications. And Gen AI is not ready for that. Gen AI is not your solution for enterprise applications. You want trustworthy, you want and robust AI. And that's not what Gen AI is about, right? So, huge growth in the AI model applications is going to be in enterprise AI context or mission critical application context, where decision making is an important component. And large language models, as we have now, are not the solutions for that. Yeah, so okay, this is the prediction. By 2027, over 50% of Gen AI will be used by enterprises, and they'll be industry or business function specific. So in our case, we use the word custom or targeted models. The models that we want to develop are tailored for or customized for or targeting very specific application, let's say clinical decision support or personalized treatment plans, personalized AI. And the Gen AI is just not your solution. So now what? Here are, sorry, bunch of some of the key shortcomings of large language models: limited accuracy in complex decision support requirements. So there is this paper, I think it is in Nature. It showed that only 56% accuracy in medical queries, right? You should not be using a system for medical application that has 56% accuracy, right? That's almost awesome. Another very important thing is inability to handle and follow guidelines. See, a human, such as a clinician, is required to follow the medical practice guidelines or clinical practice guidelines. There is a clinical practice guideline for cardiovascular disease management, clinical guidelines for asthma management, clinical guidelines for virtually any types of disease, right? And that they have to follow. So if they are going to use AI system, you have to make sure that the AI system adheres to the same guidelines or regulations or law that a human decision maker or actor has to follow. So Kaushik and I wrote a paper on value-inspired AI. And by value, we meant that in a society, we have laws, we have policy, we have regulation, we have guidelines, we have protocols. And how do you make AI system adhere to those constraints, right? Those behaviors constrained by that. Large language models are fairly broad. They consume common crawl or anything that they can find on the web. Well, for many practices, that's a medical practice. So in many other domains, law practice, you really have to have deep domain specific experience, and the generalities that you find in the web data on which the models are trained, it's not the right thing to depend on, right? So today, when you use ChatGPT and get an answer about something, it might look impressive because the language is very refined. No doubt that in language generation, these models have done an amazing job. But actual content, the veracity of that content, the factfulness of that content, that's, only if you carefully look at the answer, you understand. Many answers would be generic. Your question will be very specific. Your question will be very specific to a particular symptom that you are facing and that you are facing, not somebody else is facing. And the same symptom may have different meaning in different contexts for different people. So you brought to bring in the personalization, domain-specific aspects of it, and of course, harmful and biased content. Today, if you look at large language models, so much of the effort is spent on toxicity, harmful content, bias, hallucination, all these kind of problems, right? And there's no solution to hallucination problem by and large. A little bit of mitigation you can do. So you can't rely on these large language models for such decision support applications. So in our case, what we are advocating is that uh, we want to train our models on curated, customized training, data, knowledge, and expertise. Our word of use neurosymbolic is important in that, unlike data-driven large language model or generative AI things, we strongly believe in the role of not just data. Data alone is not enough, but data, relevant data, relevant knowledge, and relevant human expertise. All the three have to come into picture. And further, an important thing is that human expertise, even the generative AI uses human expertise. That is what they use for RLHF. But the amount of knowledge that is captured, and the context that is captured, when you are providing reinforcement, is very limited, very narrow. There needs to be more high fidelity, high bandwidth capture of human knowledge, as you might, as the word instructibility will apply, for example, right? And the use of human expertise and knowledge is not just for improving the quality of results, as is primarily done in the GPT, ChatGPT context, but also in verification for the safety purpose. For the explainability and safety purpose, you need to have specific harness, specific guidelines and specific evaluation methods to make sure the models are behaving in a robust and trustworthy manner. So we advocate use of knowledge for accuracy and unambiguous knowledge capture, capturing domain-specific information. There's a term that is widely used, world model, symbolic representative of the facts about the world, and a symbolic representative of decision process and constraint or values. So, for example, there is a specific set of steps that a clinician would go through for diagnosis and for treatment planning. It's not arbitrary. It behooves on the clinician to conduct certain labs before making up a decision, right? It's important to rule out hyperthyroidism before taking the giving the diagnosis of hypertension. This kind of stuff, right? So those need to be part of the process that the AI model has to satisfy. And the human expertise, I already made some point about it. The 2 points, important points. So we want to bring together and basically harness both the on the left hand side, you see the use of vectors and very efficient learning from data and explicit knowledge. And another term that is very well known is system 1 or perceptual computing, I call, and system 2 or cognitive computing, as I call, right? And to support both of them. So many tasks, especially in decision making, requires you to tap into the data, but it also requires you to plan, reason, and make go through a deliberate process to support decision making. And the applications that we talk about involve textual data, involve images, involve sensor data, and the whole. I think this is my most important slide. I must admit that I feel that this is a very important way to recognize where we are in the AI. For building robust and trustworthy AI systems necessary for mission critical applications, enterprise applications, uh, you know, health applications. There is a lot more that is needed that generative AI approach does not have. Recently, there was an NSF AI Institute proposal, and basically they indirectly they required us to address grounding, instructibility, and alignment. But beyond those, there are a whole bunch of them, and you can see the whole list of this, what I call hashtags, the critical characteristics and capabilities of AI model, that what an AI model should support. And I've been deliberately, my group has been deliberately pursuing that agenda, talking about each of them. Only one that is been missing that we not talked about here is abstraction. It's a very challenging problem. And long-time researchers like Team Finine, will very much appreciate what the importance of that. But all these others, and you'll find our articles, and each of these articles discuss the limitations of purely statistical methods, statistical AI, and why and how neurosymbolic approach can support this. Excuse me. Here is a picture from a paper, Neurosymbolic AI, why, what, and how. And here we give a taxonomy, or and depict the variety of options you have for combining statistical and symbolic AI methods. And I won't, describing these in detail will take a lot more time than I have now, and it's not the core purpose of our tutorial here. But you can see variety of algorithms have been developed in different way of combining these things. In one of the papers, I talked about shallow knowledge infusion, semi-deep knowledge infusion, deep knowledge infusion. And this is another taxonomy here. But but I'll make one broad comment in that the community that is represented here and allied communities have broadly followed two representational forms. One is logic, and other is knowledge graph centric. Now, I was part of the semantic web community from its very start. I had a patent on semantic web related things in year 2000, 2001 for semantic search, browsing, personalization, advertisement. And there was a part of the semantic web community that advocated use of logic and description logic in particular, and I was not a believer in that. I was a believer in graph-centric thing, property graph or RDF. My second company, Tali Semantics, utilize very large world model representation for knowledge and or knowledge graph, and it was far more scalable. So for industries have also, I don't see a substantial application of logic-based approaches in semantic web today in practical applications. And I also have the same belief that for neurosymbolic AI, you're going to involve large amount of knowledge flexibly represented, and for scalability and many other reasons, you will go with the knowledge graph kind of representation. And here, so there are a variety of ways of fusing knowledge and combining knowledge, and those things are discussed. So with that, as an introduction, I will now pass on to Megha. So what we are going to do is to take, recently we have built 4 significant applications to demonstrate the need of the class of new generation of new class of AI models that we are talking about. The neurosymbolic, compact, custom, and agile. There are 4 terms that we use now. Neurosymbolic, which I defined, targeted or custom, compact. There are also a lot of people working on small models, age deployable in a patient's mobile phone or doctor's office, and agile, ones that can be very quickly retained with low cost when knowledge, data, human expertise change, or giving instructability. So those applications are these that Megha is going to describe. And all these applications have substantial collaboration with the actual domain experts. So here you'll see, she'll talk about the group of people who worked on deploying um, school behavioral mental health across the entire state of South Carolina, because there is a 2018 law about it. The second application is about, and here there will be very interesting requirement for alignment, because there are different types of users playing different roles are engaged. So it's an excellent way to describe the alignment problem and challenge you have. The another one is personalized nutrition for specific health conditions, let's say diabetes or obesity, right? And that involves multiple knowledge bases, very comprehensive, large knowledge bases, and text and image, so multimodal data. And so that is another kind of requirements that that application faces. The third one is in smart manufacturing context. It's also multimodal, but it has sensitive data and high throughput data and continuous, evaluation. And AI model is processing these, continuously incoming data. And the fourth one is in library sciences. So we have done, and if you go to our website or our YouTube channel, you'll find videos that describe each of them. Today, we are going to describe one of them so that we can really make this concrete. Megha.
Thank you, Dr. Shet. Hi, everyone. I'm Megha, and I'll take up the next two parts of this session. So the first part, I talk about our use case example, which is the multi-tiered system of supports, or MTSS. So what is MTSS? It's a three-tiered, state-mandated framework for providing mental, behavioral health for students in school. And this is done by a support network, which consists of educators, administrators, counselors, or family members. The three tiers in the MTSS framework are Tier 1, which is the universal support, which basically consists of your general core instructions for a better social, emotional learning. This has basic moral values and behavioral tendencies that should be modeled within a human or within a child in school. Tier 2 is targeted interventions, where students who are suffering with specific troubles, for example, substance use, for example, maybe they come from broken families, maybe they have anger issues, specific areas that are troubling to these students, they are enrolled in the second tier, which is for focused or targeted interventions. And finally, the third tier is a more intensive intervention in which there is a one-on-one session with the student and an external clinician or a psychiatrist or a medical professional. That being said, let us look at an example of what happens within the MTSS system. So John is a student who is exhibiting some anger issues in class. The data that we have is, in a staff meeting, we have seen that John, who is a young child of age 16, is showing anger issues. The school counselor has the information that, okay, Mr. A teaches anger management class. So the school counselor decides that we should put John in Mr. A's anger management class. At this point, the school administrator comes and says that, yeah, that's okay. But since John is only 16 and he's a minor, so there has to be an MD present. having an MD present in classes requires budget. And at this point, John's parents might come and say that, oh, we don't have the budget to support this. And the school admin says that, okay, the school has some budget. Now, this was just a toy example to show what happens for each student, for each case. And you saw that this conversation just took like 4 turns. However, there are more complex cases which take several turns to make the final decision and reach a satisfactory resolution for each student. And this problem is added on by the fact that we are really low on human resources. This statistics of 2020, according to the American Medical Association, the recommended ratio of schools counselors to students is 1:250. But in South Carolina, where we are implementing this, the ratio is 1:336, and similar numbers all across the states of US. And this shortage a very inevitably leads to the delay in the effective intervention. And by this time, the student's mental health might get a lot worse, right? So we need timely interventions. We need to help the students better, faster, in an effective manner. So can we build a decision support co-pilot so that this entire conversation that you saw can be facilitated smoothly? Can we automate some of the processes that don't need human beings present? Can we do more with AI? So now we come to the third part, which is the vision for MTSS. Let's look at a more complex case. So let's meet Amy, who's a female of age 19. She has a history of alcohol abuse, and she has been diagnosed with depression. She is seeking support for depression and academic frustration. With this knowledge, and this knowledge is shortened for the sake of the slide, however, in reality, there are case scenarios and case files for students which have a lot more details about the student's family background, their educational background, their economic background, and their medical health, family medical health, all of that. In the real world scenario where we don't have an AI powered automation machine or an AI powered co-pilot, what usually happens is Amy, who's the subject here, has to interact with her addiction support group, with some external clinicians, with the school counselor, with her parents and school administrative. And there is a huge network or a chaos of conversations that happen back and forth just to help one student. And often, like we mentioned before, this process gets delayed a lot. So what do we, so we decided that we want to build something that will help automate the process of, carrying out the entire MTSS intervention framework. However, before showing what we ideally expect or why neurosymbolic custom compact co-pilots are important, let us take a look at how your generic Gen AI LLMs fail to solve these complex cases. So we tried this prompt and we tested on some open source LLMs and we see the responses, right? So the prompt says, I am a school counselor. We implement MTSS framework in our school. One of our students, Amy, has a history of alcohol abuse and is diagnosed with depression. She is seeking support for depression and academic frustration. However, she often prefers to isolate herself and doesn't like to talk about her emotions. How can I, along with the MTSS team, help her? So before I move on to the next slide, I would like all of us to consider a few things here. The user is identifying themselves as school counselor. That is important because that tells the domain of expertise of the user, what their inherent knowledge might be, first. Second, we specify that she's seeking support for depression and academic frustration. We also know that she has an alcohol abuse issue, which, if you recall, is targeted in the tier 2 intervention, which is for focused groups, focused studies, right? So in an ideal response, you would want the model, the AI model, to take into consideration all of these facts and give very concrete answers, not generic, right? But what are some of the responses that we got from Gemini and Meta AI? So Gemini seems to say things like, build a strong relationship with Amy, offer her different ways to express herself, encourage her to participate in activities. These are very generic responses. These are very non-professional responses. Are these really going to help Amy or the school counselor? Does it provide any concrete, measurable steps? Not really. And it doesn't even talk about MTSS anywhere, right? Meta AI does a little bit better where it shows that it has knowledge of MTSS and the 3 tiers of intervention that it supports. Yet in this particular case, it's not personalizing its answer to Amy. It is not taking into account that the person who is asking the question is a school counselor, right? So what are the problems? Very generic, non-professional responses, not personalized to Amy, not aligned to the user or who is the school counselor in this case. This is the part where alignment comes to plays a very important role. If you recall, Dr. Shet just talked about this in a couple of slides before of why alignment is a key aspect to be considered while building AI models, right? So what is an acceptable response? And this is a partial expected response, which goes something like this. As a school counselor, you might want to take the following actions. Make sure that Amy is in tier 2. Make sure that she's being active in tier 2. Talk to her on a regular basis. Now, these are the things that I am saying out loud just to exemplify what we want to happen. So she needs to be in tier 2, and she also needs to be in tier 3. Why? Because she has been clinically diagnosed with depression. So she needs professional medical attention, either from a psychiatrist or from a therapist or a combination of both, right? So what we are trying to build here is a co-pilot that says that I can work with you and the rest of the MTSS team to support with continual screening, progress monitoring, and database decision making to help Amy. Here are some concrete steps that we can take as a team to help Amy. Following that would be steps that the school counselor needs to take, the school admin needs to take, teachers and family needs to take, right? So this is what we are visualizing. Instead of the previous chaos of network that was happening where conversations are happening back and forth, there are delays in timely, effective interventions or help. Instead, we propose to build the MTSS AI concierge. Now, when we say concierge, this is a term that we coined along with our collaborators at the School Behavioral Health Academy or at U of SC. What this concierge is expected to do is to talk and interact with each of the people in this cycle from time to time, make connections to the different people. So for example, if Amy's talking to the concierge and she says, hey, I need help with this, that, what do I do? And then the concierge says that, okay, let me contact the school administrative and see if they can help you. Things like that. How do we propose to do this? So this slide right here is the big picture or the vision of how we are going to solve this problem, right? So in the center, you see the the 5 core elements of MTSS. So the first one is the framework itself. The second is teaming, because you have different team members. You have your counselors, you have your educators, you have your administrators, the family. They all need to come together and sit and discuss. And that's not always going to be easily possible because everyone has very busy schedules. Screening, obviously, because you want to keep on assessing how the students are doing, and this has to happen across the entire academic year. Progress monitoring. Through the screening and the assessments, you track how they are doing, if there is any improvement, if they have started showing worse behaviors, there is need to change. And that is when you take into consideration database decision making, right? So these are the 5 core elements, and how we provide an AI solution to them is the first one, the AI Copilot MTSS coach or concierge is going to act as the interface between the various teams and an interface between the various teams or various people who are in the framework, right? So we talk about, okay, John will be part of, if you remember from the example before, John needs to be part of the anger management class, but John is 17. So this entire thing, this entire conversation requires reasoning, right? You need abductive and deductive reasoning. You need to know, and this reasoning will come from knowledge, domain process knowledge that has to be grounded in the model, right? So there are district protocols that says that if a student is minor, then they must be accompanied by a professional. This protocol or this rule is present somewhere in the books, but the people in the MTSS team need to know that, and they might not always know that. So when we were discussing during the inception of this entire project, when I was talking to my collaborators at the SBHA, I asked her what is the biggest problem with implementing MTSS without an AI or without these kinds of solutions. She said, people don't know what they don't know, right? So how will you make better decisions? However, all of that knowledge is there somewhere in the books, in documents, etc. But you need someone to tell them that, hey, okay, if this is your problem, this is what the rule says, and this is what you do. That is grounding, right? You need your model to be grounded in solid domain knowledge. Through that, you can then do reasoning and lots of other things. Moving on, we also want the model to be aligned, meaning when the model is interacting with the different users, it needs to align itself to their domain of expertise. So if the model is interacting with a student, then it knows that, okay, this is a student, and you can consider their domain knowledge to be like at the basic level, right? If you're talking with a school counselor or a clinician, you would know that they have some domain knowledge within the medical domain, right? If you're talking with a teacher, you know that their expertise is in education, and the model responds according to that. So that's where alignment comes into play. Then we have screening, which requires instructibility and reasoning for the model, right? So you have these automated screening tests and assessments, but how do you make sense of it? For that, if you want a machine to be able to do that, you need the machine to be capable of doing some sort of reasoning, right? How do I make sense of all this data? Once you've done that, when you go to progress monitoring and database decision making, you want everything that is going on to be dynamically updated. You want a knowledge base that is constantly being updated with everything that you have, right? That is how you will be able to in the future automate, like pull in from the future, or sorry, pull in from your history what has happened before, and then act accordingly. So once we do all of that, how do we even evaluate whether our model is performing well? So we proposed 2 types of evaluations, intrinsic and extrinsic. So under intrinsic evaluation, we have your computational measures, So, for example, we use Blue, Rouge, and Meteor for just linguistic competency of the language model that's going to be acting as the interface. We have Nubia's logical consistency as a metric. We are also going to use LLM judges to show internal consistencies within the model. And Kaushik can show you guys what the evaluation of LLM judges give us. Um, then we have path strength and similarity. These are some of the intrinsic evaluations that we have. Excuse me. And for extrinsic evaluation, we want to bring in human coaches and human experts to validate and verify the responses or the overall functioning of the model. Also make it more explainable. When Dr. Shet was talking about the need for um, not just data, but data knowledge and human expertise, this is where the human in the loop comes to evaluate your process, right? And finally, we also have some fidelity inventories from the school side who guide the decision making and implementation efforts. So let me just take a second here and talk about this. So far, the other interventions are, sorry, the other evaluations we have approached with a computer science AI approach. However, the fidelity inventories, this part of the evaluation comes from the Department of Psychology, the School Behavioral Health Academy that we're working with. And they have a way of evaluating whether the schools are implementing the MTSs correctly. So they have initially a target program, like these are the goals that we want to achieve. And towards the end of the year or at a 6-month checkpoint, excuse me, they see where they have reached, and they have their own fidelity scores and fidelity measures to quantify this. Okay. Just give me a second. So at the end of the day, we think that the MTSS AI concierge would be able to do information management and summarization, internal and external information retrieval, inference and reasoning, act as an interactive coach or an assistant coach, and it maintains privacy control. And it does all of this through grounding, alignment, and instructibility. Now, before moving on to the fourth part and handing over the stage to Kaushik, this is still at a visionary stage. We have only started implementing the first step of it. We're not there yet completely, but we sure hope to be there soon. So with that, I would hand over the mic to my colleague Kaushik, who will give us a demonstration of the preliminary Copilot that we have so far. Thank you.
Thank you, Megha. Can everyone hear me okay? Okay. What I'll start with is some background so that we're all speaking the same vocabulary. So recapping neurosymbolic AI, this is talked about in many different senses. So I want to be clear about the kind of sense that we'll be talking about. The neural network part is maybe clear by this point that you take some raw data and then you project it to some abstract vector space. And then your data is represented as vectors in that vector space. The symbolic part, on the other hand, Dr. Shat showed earlier on a taxonomy of various ways in which people have conceived of symbolic AI, from full first order logic to a decidable subset to property graphs and so on, right? So when we are talking about neurosymbolic, customized and compact copilots, they are not decoupled terms, right? Everything had to play together nicely. And so when we need compact copilots. By that, I mean of the right size. So pragmatics come into picture. You want something to be just the right representative expressiveness to capture what you need. And it's good for us that knowledge graphs have panned out well in this aspect, right? So here we see various kinds of knowledge graphs, DBpedia, Freebase, OpenPsych, and the never-ending language learner, Wikidata, and so on. So knowledge graphs have so far proven pretty effective at capturing linguistic knowledge, common sense knowledge, broad-based knowledge, and domain-specific knowledge. For example, domain-specific knowledge, an example of that would be the UMLS. It's expanded as Unified Medical Languaging System. And so let's go with that for the compact design. For customization, again, knowledge graphs are useful because customization means that you have to take your data, evolving data, and update your data structures. So a knowledge graph lends itself nicely to this kind of dynamic evolution. If you have, let's say, a higher order type of logic, then it's brittle. It's not a very dynamic structure to update easily. Finally, for the neurosymbolic part, there's a very rich body of work on integrating knowledge graphs and neural networks. And we can tap into that effectively to try and build a practical implementation of the system. On the other hand, contrasting that with, say, integration of logic-based systems with neural networks, there's relatively lesser work in that, and for good reasons. If you would like to know more about that, I'm happy to talk about it. But for now, we'll just say that the computation becomes intractable in that type of integration. Right? Okay. Now, again, recapping the examples, I'll do this very quickly. So there's a student's behavioral health issue summarized in some kind of case document. And then you have a bunch of people that form the student support network that are deciding what to do with this student's case. These people include the school counselor, the student's parents, the school administrator, and so on. So each of them are going to have their own knowledge base to work with when they are deciding on the decision. For example, here we see that the school counselor understands who teaches what in the school, right? And so then they can make an informed decision about how can you draw on the school's resources. Similarly, the school administrator understands not only who teaches at the school, but also the purview of their jurisdiction. So what are they allowed to do? What aren't they allowed to do? What is the budget for it? What is aspects like what are legal aspects? Like is it a minor and what to do in that case, right? So the school administrator understands that. And then the parent is, of course, involved very intimately with their child's issue. So the takeaway from this slide is that from an algorithmic standpoint, the method has to be such that the response from the copilot is aligned to various different kinds of user roles. And this is a non-trivial challenge, right? Okay. The last part of the recap is this, the whole vision. Megha did a great job of explaining this, so I'll not dwell on this for too long, and we'll come back to this later. Okay. So first, before I show the implementation that we have, I'm sure this is a question on a lot of people's mind. Why don't we just use RAG, right? There are several issues with using RAG. One is maybe by now you have a good picture of the heterogeneity of the information in this type of setup, right? In RAG, what essentially happens is you expect some kind of uniformity in your database, and therefore you can take advantage of techniques like chunking. So you break up your database into smaller units, and now if your query is pertinent to any one of those units, you go and retrieve those units based on vector similarity. But if your information is linked across individual units, or if they are linked across different types of information across those units, RAG very quickly breaks down, right? So that's a very colloquial way of saying it, But more specifically, arbitrary chunking is an issue with RAG. And then also when you're talking about similarity across what contextual aspect, right? That's a really ill-defined notion. So then that leaves you with arbitrary thresholds. If something is greater than 0.5, let's pick it, things like that, right? And there's no customization to the user roles that we talked about. And lastly, and most importantly, there's no robustness checks. The information that's retrieved in vector space, we have no way of understanding very clearly. There are visualization techniques, but there's no clear way of understanding exactly what's going on in the semantic space for retrieval to result in the final output that we see, right? So imagine if this was an information retrieval system from the older days for this type of mission critical application, right? You couldn't get away with saying something's going on in vector space, here's your answer, right? You would have to have more guarantees than that, right? Okay. Now, we talked a little bit about representation. We talked about logic, we talked about knowledge graphs, and we talked about things in between. In more recent research, there has been a nice, let's say, innovation on how can you take a knowledge graph and transform it into a representation that language models can work with better, right? So a recent example is by Microsoft's GraphRag, that the way that they transform the graph into a text-friendly representation is they construct what's known as community summaries. So if you think of a document, let's say a paper, right? So the abstract of the paper has a certain level of information. Then the individual sections get more granular than that. And then this forms a kind of hierarchical summary structure, right? So what GraphRag does is it takes advantage of the natural hierarchy in a knowledge graph and then converts it into text at varying levels of granularity, right? Text blocks. And then you can then, if you do vector-based similarity on those hierarchical text blocks, you have something that has not only exploited the structure in the knowledge graph, but is also still in text form for the language model to not have trouble with, right? So in these preliminary implementations that I'm about to show you now, we are trying to think of what are some other ways we can bridge the gap between what a language model quote unquote understands, which is plain text, and richer forms of representation. What we've started with is question answer sets, right? So you take the initial database that you have, and using a language model, you can, or some other technique, there are methods to convert a chunk of text into question and answers. So let me. So here is an example of a knowledge base. Yeah, zoom in. Okay. Good. So here is an example of a knowledge base, right? It's a description of MTSS. I'll show you the document where this comes from. It's, as Megha said, it's a framework for supporting behavioral health outcomes in high school students. Now, what this code will do is take this piece of text and convert it into question and answers, right? And what it's using is a language model. So there you have it. Now, what is the point of this type of thing, right? With a logic-based formalism, like a propositional logic or a first-order logic, what we could do in early days is something called resolution, right? So if A implies B and B implies C, then A implies C. You can do things like this. You can do logical operations like this. In a knowledge graph, that becomes if node A is connected to node B in a certain relationship context, and node B is connected to node C in another relationship context, then the combined subgraph becomes a block of context for all those nodes, right? So how can you do those types of operations, but in textual form? So we can borrow techniques from knowledge base entailment. If we have something that looks somewhat like a knowledge base, or rather a compromise between a logical form knowledge base and a text-based knowledge base. So that's why we're, for right now, experimenting with question answers, right? As a concrete thing, what does MTSS stand for? And what is the main goal of MTSS? These are two semantically different questions, right? If they were semantically related questions, if you ran a resolution operation on these two, it would eliminate one of them, right? So that's the idea. That's why if you have a question answer based representation, you can maybe borrow some ideas from symbolic logic, right? Okay, so that's the first part. Now I'll talk a bit about the data. So this is the data after parsing through a PDF reader. Can everyone see this? Fine. Zoom in. Good. So this is a bunch of PDFs consolidated together into one document using PDF readers. Now, I'm not going to talk about the PDF reader nuances too much, but it is important, right? So this is a structured document. So the way that we process the PDF is an important aspect of this transformation. Later, if you're interested, I'll let Megha talk about it more because she's the one that handled this part. But generally what you see happen is at the end of it, there's a markdown syntax. There's different sections to this document and subsections to this document, right? So now I said earlier that we convert this into question and answers. So what that looks like. Yeah. So what that looks like is you have different question and answers for different roles, right? So the school admin is a different type of role than a clinical staff. And where is this role defined? We have data that looks like this. Okay. So when you look at any one person, right? Let's say the clinical staff, you see we have from the domain expert a description of what the clinical staff is supposed to do, which is a whole bunch of duties, right? A school administrator has their own corresponding set of duties. The school counselor has a different set of duties. So if you take that initial knowledge base that I showed you, closer. So if you take the initial knowledge base that I showed you, and just say convert it into question and answers, you'll get something that's not relevant to all of these roles, right? So what you have to input as part of the prompt is to say that this is the kind of role that I want you to transform this information for, right? Only then, when a school counselor is using this type of system, they'll have a knowledge base that is relevant to them. If a school counselor has a knowledge base that the admin understands, it's not useful to them, right? When they're trying to provide decision support. Okay, so let's see this in action. Oh, it's fine. Yeah. Thanks. Okay. So now this has become a information retrieval problem, which is that you from the original language model, you got the initial dump of text converted into role-specific question and answers. So when you type a query now, you get whatever is the closest answer matched, and then the answer is returned. Now the answer is slightly worded differently from what is in the original database, and a language model does that. I'll come to that in a second. So the answer is also represented in a few ways. One is, what are the other answers, other questions that may be relevant to the query. And the other is triples that are indicative of the essence in the answer. So for example, we are asked about responsibilities of the school administrator. And then the triple that comes up for that is administrators ensure fidelity. Now, fidelity to what? You need a little bit of domain background to understand that, but fidelity to the MTSS process is what this system is trying to say, right? There are other query suggestions that the system provides. So if we go back to the main objective, what we had is we want a copilot that's able to assist with this type of interaction, right? So what you saw just now is a specific copilot meant to assist only the school admin. You would have similar copilots for every single user role associated with the system. And that is how it is customized and aligned to those individual roles, right? Okay. So now let's go here. Okay. So the process which I just demonstrated is captured here in this graphic. You take the information, you convert it into QA sets, and then you take the query and you match it against the relevant question and you get the answer. But now, earlier I talked about in RAG a failure that had to do with arbitrary thresholds. Like how do you decide what is similar or the right amount of similar, or how it's kind of ad hoc and arbitrary, right? So there are a couple of ways that we can handle this right now. One is to check with the knowledge graph. So we understand that you get an initial set of answers to both, and then you can take those sets of answers and see if they have semantic coherentness, meaning that there is a graph path of not more than 2 or 3 hops that connects concepts in those across those answers, right? Answers that meet that criteria are good answers. The other type of robustness check is you take the answers returned by the initial search, and then you query an LLM. Is this answer answering the question, the original question? Now, this might seem circular, right? That you have an LLM and you're saying that an LLM is not good at question answering for this type of situation. And how can you ask an LLM if it is then contextually accurate, right? But the thing is, we've made the LLM's life easier, right? So we have divided up the knowledge base into role-specific question answer sets. And now, essentially, when we ask the LLM that is the answer relevant to the original query, all it has to do is look up, right? It does not have to do semantic processing so much as it has to do syntactic look, like just see if there's something similar there, right? The N judges is to account for the fact that each individual LLM at any point in time is unreliable. So you may have heard the term stochastic parrots. Each individual LLM like Dr. Shet showed earlier, is a probabilistic machine. So it will predict yes, with some probability, no with some other probability. And what we're trying to do is leverage a concept called wisdom of the crowd, where if you pool together the answers of multiple LLMs, instead of stochastic parrots, you get a flock of wise birds or something. But generally, the idea is on aggregate, the answer tends towards whether or not the answer is, I mean, the particular response is contextually relevant to the question or not, right? Okay. Yeah, so the remaining slides go through the steps that I just outlined, so that when you look at the slides later, it will make sense. But now I'll try to run through some examples of what kind of knowledge representations can we play with? Because earlier I talked about knowledge graphs are a clearly useful thing. And then I talked just now about question answers, but then what else can be used, right? Because we are interested in neurosymbolic, customized, and compact models. And we don't know definitively yet which knowledge representation is at the right level of expressivity versus scalability, right? So this is then part of our experimental setup. Okay, so here we have some dummy text generated by ChatGPT for a student's case who is struggling with academic performance. They've been facing issues in certain subjects. There's a counselor involved, and the school principal is involved. Think of them as the school administrator, right? So what are the different ways in which a neurosymbolic copilot can quote unquote comprehend this information, right? So if we look at different techniques available to us today, we already saw question and answer, so I won't look at that. The simplest one you might think of is just a summary. There's a lot of information going on here. Let's use a summarization model and see what the summary of that looks like. So that's what you get. This is a T5 summarization model. And if this is good enough for your response synthesis task, then this is fine. But for the kinds of decision support that we have seen so far, this is probably not good enough. You need something more logically expressive, right? So if you use a syntax-based, so this is constituency parsing based relationship extractor, you get this. So you find that there's a he, they're facing issues. There is a counselor that is suggesting tutoring, which is okay. So you can think of this as the brain of the machine. This is all it got from the text, right? Using this technique. And then if you look at the latest and greatest in transformer technology for graph extraction, takes a bit longer. This is what you get. So everything's connected to everything under the same relationship context. So clearly, there's a lot of work to be done here in representing the case so that the decision support is effective. The question answer case, which you already saw, is our preferred one so far. So that's why we went with it in the initial demo. Okay. What else can we toggle, right? We saw knowledge representations. Now, there are ways in which we can visualize alignment because we understand that the response has to be tailored to the end user, right? So let's have a look. Okay. So here is how we interpret this result. First, the things that went into constructing this result is shown below here. So what we feed into the Copilot is the description for each end user. So we have clinical staff, school counselor, school psychologist, and teachers. And then what we also feed to the system is the case scenario itself. And the third thing that is behind the scene that you don't see here is one of the knowledge representations that I just showed a minute ago. And what the graphic now represents is an overlap. So this is your case scenario. If you picked a knowledge graph-based representation and a BERT-based neural network, so because this is a neurosymbolic system, you have to pick one for each of those. What we find is the common words that both BERT highlights and is also captured in the knowledge graph are these green words from this case, right? And we also find that when you project the similarity across both of those into this two-dimensional space, we find that for this case, the school administrator is the most relevant to handle this case. That's why it's marked in blue, and it's also visibly closer to the representation of the case. The red ones are not all irrelevant, but they're not as pertinent to this person's case as the school administrator. That's what the system thinks right now. That's what you interpret this result to mean, right? So this is a concrete way to visualize user role-based alignment of who should handle this case, okay? Okay, moving on. So that what you saw so far is one timestamp of response generation as pertinent to the case, the student's case, also tailored to the end user that is looking at the student's case. But we have to do this over time, right? Because you saw in Megha's earlier slides that this is an interaction that happens over time. And the resolution is usually not satisfactory in the first interaction. It takes quite a few turns. So then there is a notion of a state. What is the current state of the conversation so far? And we have to model that. And we're working on that right now. In the last few days, we had a position paper that talked about a few ways in which we can do this type of state tracking, conversational state tracking. If you, let's say, use ChatGPT regularly, then you see today that they have a mechanism for retaining session memory, right? So when you log back into that same session and resume your chat interaction, it has some mechanism to recollect the state of the conversation up until that point. That mechanism is a summary. And now what we are trying to do is upgrade the mechanism from just summaries or RAG-based retrievals to something more logically expressive for reasons that I stated earlier, that you need the logically expressive recollection of the state because you want to be able to do things like check if the information has stayed consistent. Is it reliable? Is it verifiable? Can you trace it back to why it was originally talked about, right? Okay. So we'll end with two demonstration videos that hopefully generalize everything we've talked about today to other application domains. So we already looked at the MTSS use case so far. So let's look at another one so that we understand that this is generally not tied to any specific use case. Okay, so I'll narrate over it because the sound is not coming. So this is another copilot called Nourish, and it has to do with nutrition assistance, right? So nutrition decision support specifically for diet management. The customized aspect of this is we focus exclusively on the nutrition domain. You don't need to consume all the data on the internet to handle just this specific issue. The compactness is big from a couple of factors. One is that if you curate the data, then you have a smaller model naturally. And then if you also have neurosymbolic mechanisms for reasoning and learning, you also have a smaller model. Roughly speaking, the reason for that is neurosymbolic mechanisms allow discrete learning and reasoning, whereas neural network-based mechanisms need continuous spaces for gradients. And that's why those models have a large bloat, right? Large number of parameters. So the compactness arises from the curated data, the neurosymbolic learning and reasoning, and also from leveraging knowledge and human expertise, right? So you give the model a lot of assistance in addition to the data. So what you end up with is naturally small in size. Okay. So like in the MTSS case where you had very specific roles, counselor and parents and administrators and so on. Even in this case, you have every person is different, right? In what they like and dislike in terms of their food preferences. So you have a similar scenario here. Yeah, so this is a more concrete picture of what we have on this application so far. What we have built so far is a query handling mechanism that goes through multiple aspects of a recipe. As we do that, we construct a process graph, which takes the text-based recipe description and builds a process graph out of it. What is the procedure by which this recipe was obtained, right? In addition to the ingredients and other declarative aspects of the recipe. Now, combined, both the process aspect and the declarative aspects give you a semantic picture of the recipe that your neurosymbolic reasoner can then use. Right? The human expertise in this case comes from well-known nutrition databases. And so we also use that as part of the neurosymbolic reasoner to ground the reasoning in optimal outcomes. Yeah, finally, this one is when we are building a neurosymbolic AI system, customized and compact AI system, we need something like an automated ML flow pipeline. Today, what Hugging Face and other similar platforms allow you to do is they have a very mature pipeline for you to build your own model, save the weights, load the weights, do inference, transfer it to some other domain where you want to use the same model for a similar use case and so on. So the software development lifecycle for these types of models is very mature in the neural network literature today. And we need something similar for neurosymbolic customized and compact AI because there's a lot of moving parts, right? There's the neural network to choose, there's a symbolic aspect to choose, there's the data knowledge and human expertise to choose. And so we need a pipeline that has the same level of rigor as any other software pipeline to be able to do all of this without losing information and staying robust and being able to verify what we did at what point in the model development lifecycle, right? Okay. So we are drawing inspiration from a framework known as the Common Metadata Framework. The reason for doing this versus MLflow is MLflow is a model-centric pipeline design, and Common Metadata Framework is, on the other hand, a process-centric pipeline design. So the advantage that gives you is you can say that I have this high-level description of a process, like I need this MTSS setup versus I need a nutrition setup, and now give me the ability to build a neurosymbolic customized compact. So that is more helpful than saying I have a particular model that I'm starting with. Can you give me the pipeline to build this model and store its weights? So a process-centric pipeline design is more useful. Those are all the added advantages that you get from process-centric pipeline design. Okay, I think that's all we have for now, so we'll take any questions.